Hi everyone, this is Manas, your friend and tutor, and guys, this is going to be lecture 2, bending of beams on the subject mechanics of solids. So if you haven't seen my previous video, go ahead and watch it. I'll link it up in the description, and there I had explained the entire in-depth analysis of a beam which is supposed to bend, what are the different parameters which really explain the behavior of that beam, and also finally we had derived the Flexure formula which sort of connects the bending moment at a cross section with the bending stress, right, which actually varies from the neutral axis. At the neutral axis the bending stress is 0, but as you try to move away its magnitude increases. Okay, and as far as this particular case is concerned, you can see the beam would be bending in somewhat this fashion. So the fibers over here above the neutral axis will be under compression, so you'll be getting all the negative values of stress above the neutral axis, and below the neutral axis you will be getting all the positive values. That's quite true, and you'll see that we'll sort of develop an equation also. Okay, number one tip: whenever you come across any problem on bending of beams, you first need to work out the location of the centroid. Right, listen to this once again. Whenever you come across any problem on bending of beams, the first objective is to work out the position of the centroidal axis, or work out the position of the centroid, let's say, because the centroidal axis is your neutral axis, and with respect to the neutral axis the entire Flexure formula is based. Okay, and then we also need to work out the area moment of inertia. We'll come to all of those things one by one. So I'll be discussing only one example in today's lecture, but trust me, if you can understand this, then you can solve 10 more examples or unsolved problems from whichever book you follow. Right, so this is a clear-cut case of pure bending or symmetrical bending. Let's jump right into it. Front view, side view, and this is the larger version of the side view where all the dimension of the I section, this is basically an I beam, all the dimensions of the I section have been given, right? Everything has been mentioned, and you can clearly see that this beam is symmetrical about this point. Okay, so if I can just draw a line which sort of divides this entire I beam into two equal portion, right? The above portion is exactly a mirror image of the bottom portion, and if you want the vertical line, the vertical line will pass through this very point. Okay, and this point lies at a distance of, this is 250, half of 250 is going to be 125, either from the left or the right of the I beam. So if you can just draw that vertical line, so the portion of the I beam to the left of that vertical line is exactly a mirror image of the portion to the right. That's quite true. Anyway, but what we are really interested in is the neutral axis, and this is the neutral axis about which the bending moment is actually working. Let me just show you with the help of a 3D diagram. The beam actually is something like this. I don't know if I'll be able to make it properly. Yeah, something like this. Something like this. This way. That's the beam. Okay, that's the beam. That's the beam. The beam is actually like this. Somewhere here you have this point, right? And that's the neutral axis. Neutral axis. And a line passing through this along the length of the fiber, that's the longitudinal axis, and I've explained you all of these things. Longitudinal axis, and this, by the way, is going to be your axis of symmetry. Okay, I think we have spoken a lot about all of these things. Anything, the portion of the beam above the longitudinal axis under compression, the portion of the beam below the longitudinal axis under tension, above its compression. So the first thing, guys, which we need to work out is the absolute maximum bending stress. Let me mark this. What is this? A, maximum bending stress. So maximum bending stress, we've already seen in the Flexure formula, is equal to mc over I, the area moment of inertia, but always remember with respect to the neutral axis. With respect to this neutral axis, because it is with respect to this neutral axis this bending moment is actually happening. Yeah, this bending moment. Right? Now we need to find the maximum value, so you need to find the maximum value of bending moment also, and with respect to this beam you have to draw the bending moment variation. Guys, number one thing, anybody who wants to learn bending of beams and its concepts and its application, you first need to go through the concept of shear forces and bending moment diagrams. You should know very well how to draw the bending moment variation in case of a point load, in case of a uniformly distributed load, in case of a triangularly varying load. Once you know all of these things, then the concept of bending of moments will become very easy to understand and will become very easy to apply. Okay, let me just rub this off. Right. Let me show you something. This way, and let's try to draw a bending moment diagram. Okay, so this is uniformly distributed load. The bending moment diagram would be something like this. The bending moment, in fact, would be maximum somewhere here. Let me just show that. Will be maximum, will hit a maximum value somewhere here. Okay, and this magnitude is WL square by 8. That's the value of the maximum bending moment. If you just try to plug in all the values, W, well, that is 5 multiplied by L square. How much is the length of the beam? 6 square divided by 8. If you just try to work this out, 5 into 6 square by 8, let me see. I've done this already. This is going to work out as 22.5 kilonewton meter. Let me write it. M maximum bending moment is equal to 22.5 kilonewton meter. And let me tell you the reason why. This is in kilonewton per meter, right? In 1 meter, so much kilonewtons, multiplied by a meter square and divided by again what is this? WL square by 8. Okay, this does not have any unit, so that is going to cancel out. So kilonewton meter remains. That's it. That is the maximum value of bending moment. So this is something which we already know. Maximum value of bending moment is already known to us. I don't know how many of you remember this formula, and if you do not, then watch this. This one's for you. And remember this. Just take a look at this. That's a beam, W per meter. So here, once again take a look. In 1 meter it is W. In 1 meter it is W. So for a distance of L, it is going to be W into L, isn't it? For a distance of L, it is going to be W into L. Let's say, let us generalize stuff. This is L. So in center, right at the center, you can replace all of this UDL by placing a point load at the center having the same effect and same magnitude as the UDL, that is WL. So obviously it is going to divide equally. This is going to be WL by 2. Done. What we need to work out is the bending moment at any cross sections. Okay, let's say we do a section over here. We do a section here. Right? Anyways, just forget about this. Again, put up a load. Right? So we know that here it is WL by 2, here it is WL by 2. That was just an analysis. Let us do a section, and this much of the portion is visible to us. That is WL by 2. This is the uniformly distributed load. And guys, this is the section where we need to work out. Let us say this is PP dash. This is the section where we need to find the bending moment. MPP dash is equal to, just take a look at this. How would this load bend the beam? In this fashion, isn't it? Sagging case, positive, WL by 2 multiplied by this distance. Let's say this distance is X. Since this is the first problem, let us start with the basics. Let us start with the fundamentals. That is why I am telling you all of these things. WL by 2 multiplied by X. Okay, so this is over. What about this UDL? The UDL magnitude for 1 meter, it is W. So for X meter, it is going to be W into X, which is going to act right at the center. Right at the center. That means at a distance this much, at a distance of X by 2. So this is trying to bend the beam in this fashion. This is a hogging case. So minus W into X by 2. Just try to solve this equation and something beneficial is going to happen for us. So guys, this is going to be WLX by 2 minus WX square by 2. Okay. We know very well. That's the master equation, by the way. MPP dash. That's the master equation. You know, at X is equal to 0, the bending moment will be at this very point. Let's say this point is A, this point is B, and somewhere at the center, let's say that there is a point, that is point D, point C, let's say. Right? So at X is equal to 0, put the value 0, 0, bending moment at B is going to be equal to 0. So what we want is the bending moment at the center. That is at L by 2. Just try to plug in the values. WL by 2 into L by 2. So moment at the center, that is C. WL by 2 into L by 2. Done. Minus W into minus W by 2. Again, this is going to be x square, L by 2's square, it is going to be L square by 4. And there you go, this is going to be WL square by 4 minus WL square by 8. If you take the LCM, this is going to be 32, 8 4 is 32, 8 over here minus 4 over here, the common is WL square, and there you go, 4 above, 32 below, 4 8 is 32. So the final value work out as WL square by 8, and this is the basically the classical way of finding the bending moment at any cross section. You try to frame an equation and just keep on plugging the value of x, right? Okay, so that's why this is 22.5, and let me write it here, kilo Newton meter. If you want to note something down, do note it. I'm going to be rubbing it off. Right. Now this becomes a very simple problem for us. In some of the problems, you'll see that you need to work out the location of the centroid, the location of the horizontal centroidal axis, you can say so, right? There you have to apply the concept of centroids. Anyway, this is a symmetrical problem, symmetrical about the horizontal as well as the vertical, so you don't have to do that job. And you know very well that the maximum, you see this, maximum, this fiber, so the fibers along this cross section will be undergoing maximum tension, and the fibers along this cross section at this portion, at this height, will be undergoing maximum compression. Here it is going to be maximum tension. So let's say that C, you can take C as 170, you can write it over here, C as 170, that's it. That's pretty simple, right? You have to keep the value of C as 0.1 simple, and we know very well how much bending moment is. It is this much, 22.5. You need to know what is INA, and that is a bit tricky. So watch this, INA, moment of inertia, area moment of inertia with respect to this neutral axis. So let me divide this. Let me say this is rectangle 1, this is rectangle 2, how much? 20 by 300. This rectangle 1 is 250 by 20. Rectangle 3, well, by the way, is this, that is 250 by 20. Right. So what we can essentially write is INA is equal to INA1 plus INA2 plus INA3. Right. Time for some flashback. Parallel axis theorem. Just take a look at this. Flashback time. Okay, some of you might even remember this, how to find the area moment of inertia of a rectangle with respect to its own centroidal axis. Just watch. Let's say we've got a rectangle over here. That's B and that's D. Obviously, its centroid is going to be somewhere here. Let's say this is X, this is X. If somebody asks what is the moment of inertia of this rectangle area, whenever I say moment of inertia, okay, and especially in the environment of bending of beams, we should understand by default it is area moment of inertia and not mass moment of inertia. This is equal to B D cube by 12. Now if I ask find the moment of inertia, area moment of inertia with respect to this axis PP, in that case you need to apply the parallel axis theorem. Let's say this is at a distance D, or let's say this is at a distance of Y. In that case, moment of inertia with respect to any axis is equal to moment of inertia with respect to its own centroidal axis plus the area multiplied by the distance between the two axes, and here it is y and its square. So this is exactly how you can apply the parallel axis theorem to find the individual moment of inertias, that is of 1, 2 and 3 with respect to this centroidal axis, and then you can finally add them up to have the final moment of inertia of this entire I section. Right? I hope this is clear. If you want to note this down, do note it. Here we go. And let me carry out this stuff right here. NA1 is equal to NA1 with respect to its own centroidal axis. This is its own centroidal axis. How much is the moment of inertia? B D cube. That is 0.25 into 0.02 cube divided by 12 plus area 0.25 multiplied by 0.02, 0.25 multiplied by 0.02. Remember, I with respect to any axis is equal to I with respect to its own centroidal axis plus area multiplied by the distance between the two axes. That is exactly what we are doing. With respect to its own centroidal axis, you want the moment of inertia with respect to NA, of this figure, right? So you first need to work out the moment of inertia of this figure 1 with respect to its own centroidal axis, that is BD cube by 12, right? Everything has been converted in meters plus the area 0.25 into 0.02. You can understand the conversion multiplied by the distance between the two axes, and you can clearly see this is the distance between the two axes. How much is this? 150 plus this is 10, this is going to be 160. So let me write it over here. This is 160. So 0.16 and its square. Okay. Then I Na2 calculation, that is pure mathematics. I don't want to get into that stuff. I Na2, watch this. The neutral axis actually coincides with its own centroidal axis. Once again, the neutral axis, when you talk about figure number 2, when you talk about this second rectangle, its centroidal axis is right here and the neutral axis is also right here. So there is absolutely no distance, no gap between them. Anyway, we'll just try to plug in the formula. The base is this 20. So 0.02 multiplied by this height is 300.3 BD cube divided by 12. Even if you want to apply the parallel axis theorem, you can do that. This is going to be 0.02 multiplied by 0.3, and you can see there is the centroidal axis of this figure 2 overlaps with this neutral axis, so there is absolutely no vertical distance between them. So it's going to be 0 and its square. You can have a value. Obviously this is going to be 0, right? Not 0. This much term is 0 and there is going to be some non-zero value over here. We'll get to that. And finally I Na3, very easy. Again, same rectangle. These two are quite identical, isn't it? So same stuff, 0.25 multiplied by 0.02 and its cube divided by 12, and then the area 0.25 multiplied by 0.02 plus 0.25, not this way, that's the area, distance between them. The centroid would be here. The distance obviously is going to be this much, and that's, by the way, is 160. 150 plus 10 is 160. So it's going to be 0.16 and its square. Okay. So let me now plug in all the values. I neutral axis 1. I have already worked it out. This is 128.16 into 10 raised to minus 6. 128.16 into 10 raised to minus 6. Okay, what about INA2? How much is that? This is 45 into 10 raised to minus 6. INA2 is 45 into 10 raised to minus 6. Plus, again, INA3, well, it is going to be same 128 into 10 raised to minus 128, but 128.16 into 10 raised to minus 6. And all of this, guys, the unit is meter raised to 4. So the final value of the neutral axis or the moment of inertia with respect to the neutral axis is 301.3 minus 6 meter raised to 4, and this is your I with respect to neutral axis. A very important data for our further analysis. Now, how to approach from here? We want to work out the maximum, absolute maximum bending stress. So we know very well the maximum bending stress is at the fiber which is farthest from the neutral axis. You can see this fiber is farthest from the neutral axis. How far? It's 170 mm. This fiber also, right? The fibers over here, here, also at a distance of 170. And What we'll try to do is we'll try to plug in the value of C as 0.17, that is in meters. Now we know this, so just try to plug in all the values and you can get the final answer. Sigma max is equal to, here we go, what is the value of M? 22.5 kilonewton meter. 22.5, let us keep it in kilonewton meter. C's value is 0.17, okay, outermost fiber, divided by I's value is 301.3, 10 raised to minus 6. So the final value of maximum bending stress which we are going to get is sigma max. Let me write it. How much is that? This is going to work out as 126. 12694.9, 12694.9, 12694.9 kilonewton per meter square. So you shift 3 decimal places back, this kilo will turn to mega, and obviously sigma max, you just take this value, you can write this as 12.69. so 12.69, you just write it off, it is going to become 12.7 mega pascals. Okay, this is the value of sigma max that we are interested in. Here we go. We know this has been worked out, absolute maximum bending stress. Okay, let us find this first. What is the stress at point B? Okay, stress at point B. Flexure formula. Flexure formula. Do you remember the Flexure formula? I, selfish equation. Sigma as a function of y. Y is the distance from the neutral axis. If you move upwards, take it as positive. Take y as positive. And which in our case, if you put y as positive, we are going to get the corresponding stress as negative, because everything above the neutral axis is under compression, minus my I, and by the way, this is neutral axis. Always remember, the bending moment has been applied with respect to the neutral axis. So where do you wish to find? You wish to find at point B. At point B. How far is point B from the neutral axis? So point B lies at a distance of 150. Okay, point B lies at a distance of 150. So y is equal to plus 150, and obviously if you are going to keep a plus positive value, so you are going to get a negative value of stress. Here we go. Sigma B is equal to minus, this is going to be 22.5 multiplied by 0.15. So this is in millimeters, guys. We have converted, divided by moment of inertia 301.3. 301.3 into 10 raised to minus 6. And obviously the answer that you are going to get again is going to be in kilonewton per meter square, or you can also say this is kilo pascals. Once you do the conversion, let me tell you, the final value that you are going to get is 11201.4. 11201.4. This is in kilo pascals, and I don't like kilopascals, I like megapascals. Okay, 11.2 MPa. There you go. There you go. That's it. Now let us try to make the sketch. And obviously, zero bending stress. If you move in the positive direction of y, the stress is going to increase. Proportional increase is going to be there. You see this equation, right? You see this equation. And similarly, if you move below, you put the value of y as negative. So when y is negative, negative and negative will become positive. So you will get the positive value of stress, which indicates a case of tension. Okay, case of compression with a negative sign, a case of tension with a positive sign. So these were all the calculations, and now let's try to do the final sketch. Here we go. Okay, I'm rubbing it off, guys. Just watch this. The beam is actually like this. Top portion, something like this, bottom portion, and That's the longitudinal axis, which in fact becomes your neutral axis in the side view. Okay, this at a height of 170, this is also at a height of 170. That's quite true. Anyway, the bending moment is right here with respect to an axis perpendicular to the plane of board, and that is your neutral axis, which you cannot see in this view. Anyway, we are interested in making the profile. So obviously this is your point B, this is your point D. So at point B, you know how much is this? 11.2. What about this point? This is point D. This is point D. Let me mark it. This is point B. Okay. As far as point D is concerned, there we have the maximum value of bending stress, that is 12.7. That is 12.7. This way. This way. So you can simply make it. That is the bending stress distribution. All the fibers, they are pushed inwards. That is why a compressive stress is there. And as far as this portion is concerned, here all the fibers are sort of pushed outwards, right? And you know this is the maximum stress. You know here this is maximum stress, and this is at point B. You know at point B that is sigma B, and how much is that value? That is 11.2 MPa. And how much is the maximum value? That was 12.7. So this is the sketch which we have made finally, right? So that was all about bending of beams, that was all about the flexure formula, and that was all about how moment of inertia with respect to any axis can be worked out using the parallel axis theorem. So guys, that was all for today. I'm going to see you again in the next video. Until then, take care, have a nice day, keep learning, keep watching, and thank you.